In this video, we're going to talk about properties of logarithms. That's section 6.5 in our textbook. I've written down the first 7 properties of logarithms for us here on this page, and we'll be referring to them as we go throughout this lecture. So let's start off by going through each one of the properties and explaining what they mean. So property 1 says log to the base a of 1 is equal to 0. What that means is if you rewrite this in exponential notation, your base is a, it's raised to the 0 power, and that equals 1. A to the 0 is 1, which is a true statement. So here's an example with numbers. If we say log to the base 7 of 1, we know that this answer is 0. If we say log to the base 3 of 1, we know this answer is 0. It doesn't matter what the base is. If you're taking the logarithm of 1, you're going to get 0 out. For our next property, we have log to the base a of a equals 1. To see how this property works, we again rewrite it in exponential form. So we start off with this a. This is the base of our logarithm, so it's the base of our exponential. We are raising that to the first power, and we know that a to the first power is a, which is represented in this a here in the logarithm. So here's an example with numbers. If we have log to the base 8 of 8, we know that this is 1, right? Because of 8 to the first power is 8. Here's another number example. The natural log of e is 1 because the base on the natural log is e. In our next property, property 3, we have a to the logarithm with a base of a, which is the same a in this base as you see here in the base of the exponential. The logarithm of m is equal to m. So the way that we're going to see how this property works is actually to rewrite it in logarithmic form. So we're going to take log, and the base of the log is this a right here. We are taking that logarithm of what the exponential is equal to, so that's m, and then that equals the exponent, which is log to the base a of m. To see this property with a number, we could take a base of 4, raise it to a logarithm with a base of 4 of, let's say, 3, then we know that this answer is equal to 3. For our fourth property, we have logarithm to the base a of the expression a to the r power is equal to that same r power. So the way that we see how this property works is we rewrite the logarithm in exponential form. So we take the base of the logarithm, which is a, it's raised to whatever the logarithm is equal to, which is r, and then this is equal to whatever we're taking the logarithm of, which is the expression a to the r. To see this property using numbers, here's an example. Say we have log to the base 5 of 5 to the second power. The answer is just 2, because if you rewrite it in exponential form, you have 5 to the second power, which is 5 to the second power. For our fifth property, we have the product inside the logarithm. So we have the log to the base a of m times n, and that is equal to the sum of the logarithms. So here's an example with numbers. We can say log to the base 2 of, let's say, 3 times 4 is equal to log to the base 2 of 3 plus log to the base 2 of 4. This should remind you of the rule of exponents, where if you have a base x to the third power times a base x to the fourth power, what do you get to do with those exponents? You get to add them. So it becomes x to the 3 plus 4, which is x to the 7th. And so we're doing the same thing here, except we're talking about having the same base on your logarithm. The next example should also remind you of a rule of exponents. This one is if you have the log of the quotient, this is equal to the difference of the logs. So here's an example with numbers. Suppose we have log to the base 2 of 5/3. This is going to be log to the base 2 of 5 minus log to the base 2 of 3, right? And the rule of exponents here that you should be thinking of is if you have x to the 5th over x to the 3rd, this is x to the 5 minus 3, which is x squared. So again, is if you have the same base, you can take the difference when these bases are in quotient form. So the same base is what we're getting here in the logarithmic form as well. The last property tells us that if you have log to the base a of an expression m to the rth power, you can move that rth power down to the front of the logarithm as a multiplier. So this r gets moved in front of there, and now it's being multiplied by the logarithm. So let's look at an example of property 7. So suppose we have log to the base 8 of 2 to the third power. This is going to be 3 times log to the base 8 of 2. So this 3 gets moved to the front of the logarithm, and now you have 3 times the logarithm. So these 7 properties are what we're going to use to practice with for the next few moments. And then there is actually one additional property, so there will be 8 total properties. To practice these properties, we are going to use them to expand logarithmic expressions. So for example, we could have log to the base 3 of x times the square root of x squared plus 1. And we can expand this expression into multiple logarithmic expressions using the properties on the previous page. So first of all, realizing that we have an x times the square root means that we can use property 5 to rewrite this as the sum of the logarithms. So this will be log to the base 3 of x plus log to the base 3 of x squared plus 1. So that was property 5 if you're keeping track. Then our next expansion can come from the fact that x squared plus 1 is inside the square root. So secretly, that expression really can be thought of like this. So we'd have x squared plus 1 to the 1/2 power, because the square root is a rational exponent. And then from there, what that means is we can use property 7 to bring that 1/2 power to the front of the logarithm as a multiplier. And so now we have this. So that was the use of property 7 in that line. And this is actually as far as we can take it. This x squared plus 1 right here, this is a plus. So we can't expand this into 2 logarithms like we did up here, right? This was a multiplication symbol. So this is our final answer for that example. The next example I'll do will be log of x squared over x minus 3 cubed. So you notice that I didn't write a base in this problem. So the implied base is 10, right? It's the common logarithm. Now let's go ahead and take the single logarithm and we're going to expand it into multiple logarithms. So first we're going to identify that we have the log of the quotient, right? X squared over x minus 3 cubed. So we can use property number 6 to expand this expression. So we'll have the logs subtraction, the log of the difference. So first we'll have the log of x squared, and then we'll have minus the log of the denominator. So that's x minus 3 cubed. So that was property 6. And then the next thing that we'll notice is we can again employ property 7 to go ahead and bring this exponent of a 2 to the front and this exponent of a 3 to the front. So our answer is going to be 2 times log of x minus 3 times log of x minus 3. So that was, again, property 7. Now, again, you might be tempted to say, oh, well, I can break this up into the difference of the logs. You can't, right? You can only break it up if it's multiplication or division. The next example of expansion that I'll do will be log to the base pi of the expression x squared plus 7x plus 12. So you might initially look at that expression and say, well, I just learned that I cannot expand this into 3 different logarithms because of these are plus signs and not multiplication signs. But can we turn this expression into a multiplication sign? And we can, because we can factor it. So this is log to the base pi of the factored expression x plus 3 times x plus 4. Now we can identify that the multiplication symbol is right there, and so then we can expand this further by using property 5. So this becomes log to the base pi of x plus 3 plus log to the base pi of x plus 4. And that'll be the final answer for that one. For our next round of examples, we're going to use log properties to condense each logarithm. So in the last examples, we were making them bigger. Now we're making them smaller. So in other words, we want to write these logarithms as a single expression. So let's start with this one. Log to the base a of 7 plus 4 times log to the base a of 3. We can condense that into a single logarithm because this base matches this base. We know that we can use logarithmic properties. But before we use that fifth property, we want to identify that this 4 is a multiplier on the outside of this logarithm. So we're going to go ahead and put that back as an exponent on the 4. So we'll have log to the base a of 7 plus log to the base a of 3 raised to the 4th power. Okay, so that was using that 7th property in reverse. And so a hint here, when you're condensing, you actually always want to start with that property if possible. It's like it's like order of operations, right? You always do exponents first. So then the next thing that we're going to do is use property 5 to say that the sum of these two logarithms becomes the log of the product. So we have a single logarithm, and inside that logarithm is the product of 7 and 3 to the 4th power. And so that was property 5 in reverse. And then finally, our final answer here, because these are just numbers inside of here, we can figure out how much that expression is, and we end up with log to the base a of 567. So that's an example of how we can use properties of logarithms to condense. Let's go ahead and get one more example. So for this next example, we have this nice long expression here. The expression is log to the base. No base is written, so we know the implied base here is 10, right? And that's plus log to the base 10 of 9 plus log to the base 10 of x squared plus 1 minus log to the base 10 of 5. So we have 4 logarithmic expressions here that we want to go ahead and condense into a single logarithmic expression. So we can only do this because they all have the same base. But here's how I would recommend going about this problem. So I'm going to go ahead and actually group these two sets of logarithms together, and I'm going to just kind of work in pairs. So using property 5, I know that this first pair becomes log. Again, the implied base here is 10, and it's x times 9 inside that logarithm. Plus, then for my other one, because the operation here is a subtraction symbol, we have log of x squared plus 1 divided by 5. And so now I can condense one more time because the operation between here and here is addition. What I can do is write log of x times 9, if you'll let me write 9x, times the quotient expression x squared plus 1 over 5. So now we've multiplied those two expressions together inside one logarithm. So I've done it, I've condensed it into a single logarithm, but just clean it up using a little bit of algebra. We end up with log of 9x cubed plus 9x all over 5 inside that one logarithm. The last property, property number 8, if you will, is called the change of base formula. And what this formula allows us to do is to take any arbitrary logarithm with any base a and change it to an expression with a base we desire. So we'll call that new base b. So this is what the logarithm to the base a of m equals when we change our base to b. It becomes logarithm to the base b of m divided by logarithm to the base b of a. So here's an example of how you might use this property. So suppose we want to rewrite each logarithm with a base of e or 10. And why would we want to do that? Well, because e and 10 are the bases on our calculator. So if we have log to the base 3 of 21, we don't know what that logarithm is equal to, and we can't use our calculator to evaluate it. But if we change the base to 10, we'll have log to the base 10 of 21 divided by log to the base 10 of 3. And so into our calculator, we can just type log 21 divided by log 3, and that expression comes out to be about 2.77. So what we did was we changed our base from a 3 to a 10, and the way we did that was by taking the logarithm of our new base of the original thing we're taking the logarithm of, the 21, and then we divide that expression by the logarithm with our new base of the original base. And plugging that quotient into our calculator yields 2.77. Now, what would it look like if we changed our base to an e? So same problem, log to the base 3 of 21, but now I'm choosing a base of e. So I'll have log to the base e of 21 divided by log to the base e of 3. And again, we know log to the base e on our calculator is the ln button. So we have ln of 21 divided by ln of 3. And do you think we get the same answer? Well, we should, right? Because we started with the same problem. It is. It's 2.77. So here's an example of a problem where we would maybe want to use the change of base formula and some of our other properties as well. So suppose we are looking to evaluate the expression e to the logarithm. The base of the logarithm is e squared. We're taking the logarithm of 9. So e is the base. This whole thing is the exponential. And the exponential itself is a logarithmic expression. And that logarithmic expression has a base of e squared. And we're taking the logarithm of 9. This is like exponents embedded within logarithms. This is crazy. So first, we're going to go ahead and rewrite 9 as 3 squared. And so you maybe don't know why yet, but you'll see. And so we're taking the logarithm of 3 squared, right? We were taking it of 9, now we're taking it of 3 squared. Just a different way of looking at it. Then we're going to go ahead and do a change of base on this logarithm right here. So we want to change this base of e squared to a base of e. And so if we do that, we'll have log with the new base of e of the original thing, 3 squared, divided by log with the new base of e of the old base, which is e squared. So I can write that a little bit cleaner as e to the natural log of 3 squared divided by the natural log of e squared. And this was where we used our change of base formula. And so then we're going to go ahead and use property 7, which allows us to take these exponents and move them to the front. And what you'll notice then is that they actually cancel out. So we'll have e to the 2 times the natural logarithm of 3 divided by 2 times the natural logarithm of e. So we're going to cross out those 2's. And so now, what do we have? We have e to the natural log of 3 divided by the natural log of e. Well, now we actually use one of the original properties to realize that this denominator, the natural log of e, is just 1. So that was one of the very first properties, kind of one of those simple ones. So this is e to the natural log of 3 over 1, which is just e to the natural log of 3. And then property 3 kicks in, which says that if the base of your exponential equals the base of the logarithm that is the exponential, so this base right here is the same as this base right here, then the answer is just what you're taking the logarithm of. And so this whole expression is really just 3. All right, one more example for us to work through here, just to practice using some of these properties that we discussed today. Let's again evaluate. This time, let's suppose we have log to the base 3 of 5 minus log to the base 3 of 4. And that whole expression is the exponent on a base of 3. So this base of 3 has this whole thing as an exponent. So we're going to use our properties first to go ahead and realize that this logarithm and this logarithm, since they have the same base and the operation between them is subtraction, we can go ahead and condense them using property 6. So this becomes 3 to the log to the base 3 of 5/4. So the logs of the difference become the log of the quotient. And then Now we're going to go ahead and use property 3 to realize that this base here matches this base here, so our answer is just this expression that we're taking the logarithm of, which is 5/4. So this was how the last example ended too. So between here and here was property 3, and between here and here was property 6. So hopefully this was a good introduction to properties of logarithms. In our live class, we'll go ahead and do more examples together, practicing using these properties.